Hello everyone, my name is Mahshid Alamdar from University of Texas at Austin, and today I want to talk about optimized spin-orbit torque magnetic tunnel junction devices and circuits for in-memory and neuromorphic computing. This project has been done with the help of my colleagues and collaborators at UT Austin, Applied Materials, Sandia National Labs, and UT Dallas. So today I will start with the motivation for why we are interested in studying the magnetic tunnel junctions and its applications in in-memory, neuromorphic, and radiation-hard computing. Next, I will briefly go over what three-terminal domain-wall magnetic tunnel junction is, and then we will compare the MTJ on patterned film and devices switching behavior. Next, I will go over our results on improving the cycle-to-cycle variation by domain-wall initialization, and then we study the effects of domain wall initialization on a 32-bit full adder accuracy. Next, we will see if it is possible to switch the MTJ back and forth for a few times, and finally we will show an inverter circuit using two of these magnetic tunnel junctions, and then we will wrap up with a brief conclusion. So why should we look at magnetic tunnel junctions? There are several potential applications for spintronic devices, including in-memory, neuromorphic, and radiation-hard computing. Computing today faces walls when processing data-intensive and unstructured tasks. Memory access in modern computers using von Neumann architecture can dominate as much as 96% of the computing time. So the development of in-memory computing magnetic devices could alleviate the memory wall between computation and memory on chip by implementing reconfigurable logic in memory blocks. Magnetic tunnel junction is a logic in memory device at the core of emerging MRAM technologies, with several benefits such as non-volatility, which would reduce idle leakage, and normally off behavior, which results in ultra-low power consumption. Today's von Neumann computing architectures need to access external memory, do not have enough dense memory to store information, and have serial processing, which increases the energy requirement for processing many big data tasks, such as image recognition. These tasks require processing a large amount of data, often in real time, which requires the functions to be done in parallel. One path forward is to use new computing architectures that operate closer to the way the human brain works. Our group is working on modeling, building, and measuring three-terminal magnetic tunnel junction neurons and synapses, capturing biological brain behaviors such as integration, firing, and leaking behavior of neuron, and multivariate resistance output of synapse. The emerging three-terminal MTJ neuromorphic devices could eventually be used to build neuromorphic computers and will have broad impact in the future of computing and all areas of big data. Radiation-hard computing is used for certain situations such as outer space, nuclear sites, or any other radiation environments. There are several types of radiation methods to test radiation hardness of electronic devices. Here we studied the radiation hardness of the spin-orbit torque magnetic tunnel junction to gamma and heavy ion radiation. This figure shows the magnetic hysteresis loop, which shows the device on-off ratio before and after gamma radiation. As you can see, gamma radiation up to a dose of 1 megarad has no observed effect on either of the free or reference layer behavior of these MTJs. Then we move on to heavy ion radiation, and this figure shows characteristic hysteresis loop from non-radiated sample in blue up to a dose of 10 to 14 ion per centimeter square in red. As you can see, little effect is seen up to dose of 5 times 10 to 12, but at 1 times 10 to 13 ion per centimeter square in green, the loop starts to widen, and for higher fluences, the perpendicular anisotropy disappears and it gets completely in plane. But still, these MTJs are very robust up to a high enough fluence and could be used as promising candidates in many radiation environments. So now, after checking all of these applications that can be achieved using spin-orbit torque domain-wall magnetic tunnel junction devices, let's take a more detailed look at what magnetic tunnel junction is and how it works. The MTJ stack is composed of several ultra-thin layers, including 2 ferromagnetic layers that are separated by a thin oxide barrier. The reference ferromagnetic layer, which is on top in this configuration, has relatively large magnetic anisotropy, and its magnetization direction is fixed in the reference orientation. However, the free ferromagnetic layer, which is at bottom here, has relatively low coercivity, and so its magnetization can be flipped by applied current. Depending on the relative magnetization direction of these two ferromagnetic layers, parallel or anti-parallel, the MTJ shows two stable resistance states, low or high, which define 1 or 0 states in logic devices and circuits. This figure shows a schematic of the studied three-terminal domain wall magnetic tunnel junction. A heavy metal ferromagnet oxide three-layer is patterned into a domain wall track with an output MTJ centered on top of the track. The voltage applied between the in and clock terminals moves the position of this domain wall in the domain wall track. The domain wall position determines the MTJ resistance and therefore the output current from the out terminal to the next MTJ device in the circuit. This Oersted field line electrode is used to nucleate the domain wall initial position entirely with the current. A notch is also fabricated on each side of the track to keep the domain wall from exiting the device. And here you can see the STM images of the device prototypes with domain wall track width of 450 nanometer, 350 nanometer, and 250 nanometer. Now let's take a look at the switching behavior of our pattern devices and compare them with the unpatterned film. In this figure, the out-of-plane major hysteresis loop of the unpatterned film shows perpendicular magnetic anisotropy. To better understand the switches, the magnetization vector of 4 ferromagnetic layers of the stack are shown by arrows here. The bottom green arrow is the free layer, the blue arrow is the reference layer, and the top 2 gray arrows are the 2 layers of the synthetic antiferromagnet or staff layers. Starting from saturation at positive field, as the field decreases, first the staff layers unravels due to its anti-parallel coupling, and then around 86 millitesla, the reference layer aligns with the bottom staff layer, and then at 1 millitesla, the free layer switches, and finally at minus 190 millitesla, the top staff layer switches, and they all get parallel again. And we will have a similar switches when we get back to positive field in this loop. This figure shows the minor hysteresis loop of the unpatterned film, where the field is kept low enough that only the free layer switches, as you can see. Next, the properties of 6 prototypes compared to the unpatterned film are summarized in this table. The average device TMR, which is 171%, is close to the unpatterned 168% TMR. The device average RA product, which is 29 ohm micrometer square, is also close to the unpatterned 35 ohm micrometer square RA product. These results show both the TMR and RA product are maintained after patterning. This is a large improvement over previous results where the patterning degraded the TMR to 10 to 40%. The other improvement is that our devices show up to 203% TMR, which is very close to the 200% expected highest TMR seen in perpendicular magnetic anisotropy, cobalt iron boron MgO magnetic tunnel junctions. High TMR is important in MTJs for logic applications since it determines the current separation between the 0 and 1 states. The average switching fields of the pattern devices are also compared with the unpatterned film in this table. And finally, these two figures show MTJ resistance versus out-of-plane magnetic field major and minor loops for device 1 with 450 nanometer and device 6 with 250 nanometer track width. Now let's see how domain wall initialization can improve the cycle-to-cycle variation. We first studied the MTJ switching behavior versus voltage when no initial domain wall is present. First, saturation field is applied to set the free layer magnetization in the parallel mode. Then voltage is applied through the domain wall track to switch the free layer magnetization, and they all get anti-parallel. These two figures show example MTJ resistance versus voltage for 5 cycles for 2 of the devices, and the switching voltage variation for the first device is 75%, and for the second device it is 44%. The relatively large range in switching voltage is consistent with domain wall nucleation at different defect sites each cycle. We then study the domain wall MTJ switching behavior versus voltage when electrical current is used to nucleate the domain wall at an initial position. After applying saturation field of minus 120 millitesla to bring a device to antiparallel state, voltage is applied through the Ørsted field line electrode to initialize the domain wall, which switches the MTJ from antiparallel to parallel. Next, the voltage is applied from in to clock to switch the domain wall that has been nucleated, and this switches the MTJ back to the antiparallel situation. This figure at right shows the initialization cycle-to-cycle variation of a device over 10 cycles, and here the variation is 10.66%, which is decreased from 44 up to 75% variation that we had before domain wall nucleation. Device success depends on viability in a functional circuit. We have simulated a domain wall MTJ 32-bit full adder, and in this simulation, parameter variation is increased from 0 to 25%, and the full adder accuracy is calculated and shown here. Two TMR values are used here, the average device TMR of 171% and lower TMR of 164%, to show how TMR variation affects the overall accuracy. In general, variation massively degrades the full adder accuracy. For 171% TMR, device 1 variation of 10.66%, which we got after Ørsted line initialization, corresponds to an adder accuracy of 90%. As you can see, further optimization to variation of 5% would produce almost no errors. For further details about this simulation, I would refer you to this paper by our colleagues in Sandia National Labs. In an operating circuit, it's expected the domain wall will not have to be often nucleated, since once created, it will be pushed back and forth with nucleation used to refresh the data when needed. So the right reset cycle-to-cycle behavior is shown in this figure. First, the device is saturated in the antiparallel mode by applying minus 120 millitesla bias field. After nucleation with the Ørsted field line, which causes the MTJ to switch to parallel, voltage is applied through the domain wall track to right the device, which switches the MTJ from parallel to antiparallel. Then another voltage with opposite direction is applied to reset the device, making the MTJ switching back from parallel to the antiparallel mode. This is repeated for 4 back and forth cycles, showing the domain wall MTJ can be repeatedly written and reset. Next, a 2-device circuit is set up by wire bonding output of device A to input of device B. After initializing the domain wall by sending the pulse through the Ørsted line, both devices are in the parallel state with domain walls nucleated. To then read device A while writing device B, a voltage pulse is applied between clock A to clock B, and this figure shows for 10 reinitialization cycles that the current through device E switches device B from parallel to antiparallel, with average switching voltage of 4.06 volt, which is bolded in black, and variation of 10%, while device A is still parallel. On the other side, when device A is returned to its antiparallel state, for 10 reinitialization cycles, the current through device A switches device B from parallel to antiparallel, with average switching voltage of 4.61 volt and variation of 15%. Thus, supply voltage windows has opened up between 4.06 and 4.61 volt, where on average the circuit will act as an inverter. When device A is in the low resistance parallel state and produces a high current, which means logical 1, device B switches to anti-parallel resistance, which means logical 0. On the other side, when device A is in anti-parallel and it is 0 state, device B is still on the parallel resistance, which is state 1. So in conclusion, domain wall magnetic tunnel junctions are an emerging class of magnetic random access memory-like devices and could address current bottlenecks in computing. This work overcomes major challenges in domain wall MTJ devices by showing high TMR and maintained array product after patterning, characterizing the variation in switching behavior and that it can be low enough cycle-to-cycle variation for circuit applications, and also showing bit propagation in an inverter circuit. The work provides design parameters for improved future domain wall MTJ device and circuits, and it also motivates film growth and device optimization to remove the need for external DC fields, as well as larger statistical measurements of the cycle-to-cycle and device-to-device variability. At the end, I want to acknowledge that this project has been funded by Sandia National Labs, and a special thanks to my advisor, Professor Incorvia, and my colleagues at Inc Lab of UT Austin, especially Thomas, who fabricated the device prototypes. Thanks for your attention. This is my email address. I would be happy to answer if you have any questions.